Welcome to Enzyme Kinetics. Most of you are looking at the following section and saying, hey, I learned this back in pre-med. What does this have to do with pharmacology? Well, as it turns out, most drugs work by activating or inhibiting enzymes in our bodies. So before we can understand the drugs themselves, we need to review enzymes. As you know, enzymes speed up reactions. They do this by binding their substrate, forming an enzyme-substrate complex, and converting that substrate into a final product. A simple analogy can be made between bees, flowers, and honey. Imagine that the bee is our enzyme, the flower, or pollen, is our substrate, and the honey is our final product. The bee attaches to the flower and eventually converts the pollen into honey. As you may remember from chemistry, the rate or speed of enzyme reactions depends on a few factors. One, the affinity of an enzyme for its substrate, or in other words, how well the bee can find and attach to the flower. And two, the enzyme concentration, or how many functional enzymes are around to produce product per unit time. In other words, the more healthy bees around, the more honey produced per unit time. Now let's apply our analogy to a couple of high-yield graphs. The following graph is based on the Michaelis-Menten model of enzyme kinetics. It plots velocity, or speed of our enzyme reaction, against substrate concentration. This is a graph asking how fast our bees produce honey in the presence of X number of flowers. Remember, the rate of the reaction is dependent on affinity and enzyme concentration. So let's talk more about affinity. In the world of enzyme kinetics, the Michaelis constant, called Km, is inversely related to the affinity of an enzyme for its substrate. Do you remember what is Km? Km is the substrate concentration at which the enzymes are working at 50% Vmax. Or in other words, Km is the number of flowers needed for the bees to produce half a pot of honey. For example, let's say the white honeybee can produce half a pot of honey from only one flower, while the yellow honeybee can produce half a pot of honey from 10 flowers. Which bee is more efficient? The white honeybee, obviously, who produces a half a pot of honey from only one flower. So bringing this full circle, is it better to have a higher or lower Km? That's right, a lower Km. A lower Km represents a more efficient enzyme. The lower the Km, the higher the affinity an enzyme has for its substrate. So a bee that can easily find and bind tightly to its flower will be more efficient at making honey. Enzyme concentration is the second factor that affects the rate of a reaction. Imagine this scenario. There are 5 bees and only one flower. So 1 out of the 5 bees will work to convert that pollen into 1 pot of honey. However, let's say now there were 5 flowers. Well, all 5 bees would be working to make a total of 5 pots of honey. And what would happen if there were 10 flowers? The 5 bees would still only be able to make 5 pots of honey at a given time. They're all occupied working on one flower. In enzyme kinetics, we call this the enzyme saturation point, or when all our enzymes are working at Vmax. Vmax is the maximum speed at which an enzyme can convert substrate to product and is directly proportional to the enzyme concentration. As you see from the graph, at a certain point, adding more substrate does not increase the velocity of the reaction. Adding more flowers does not produce more honey. The only way we could increase Vmax would be by adding more enzyme. To produce more honey, we need to add more bees. This is why enzymatic reactions follow a hyperbolic curve. The velocity of the reaction initially increases exponentially as substrate is added, but then tapers off as the number of enzymes becomes saturated. There are examples of enzymatic reactions that do not follow the common hyperbolic curve, and instead follow a sigmoid or S-shaped curve representing cooperative binding. Do you remember from your respiratory chapter why hemoglobin is an example of cooperative binding? In cooperative kinetics, binding of a substrate causes the affinity of the overall complex to increase, causing more substrate to bind. In the example of hemoglobin, when an oxygen atom binds to one of hemoglobin's 4 binding sites, hemoglobin's affinity to oxygen increases, aka oxygen is more likely to bind to hemoglobin bound to one oxygen over a hemoglobin that is unbound. Moving on to another high-yield graph called the Lineweaver-Burke plot. Again, we are plotting velocity or speed of our enzyme reaction against substrate concentration. However, pay close attention that we are now dealing with an inverse or double reciprocal plot of the Michaelis-Menten graph. It's Michaelis-Menten turned on its head. The x-intercept represents -1 over km, and the y-intercept represents 1 over V max. Okay, so that probably sounded super confusing. So how do we interpret a graph like this? Or more importantly, we need to understand what would happen if we shifted things around a bit. Well, if we shifted the x-intercept to the right, closer to 0, we would be making this value less negative, and km would increase. As we learned before, increasing our km would decrease affinity. So inputting numbers can make this a lot easier to understand. Check this out. As you can see, when -1 over km becomes less negative, from -2 to -1, the km increases from 1/2 to 1. Now moving to the y-axis, if we shifted the y-intercept up and farther away from 0, we would be increasing this value. But the Vmax would decrease. As we learned before, decreasing our Vmax would decrease the rate of the reaction. Again, inputting numbers can make this easier to understand. As you can see, when 1 over Vmax increases from 1 to 2, the Vmax decreases from 1 to 1/2. Okay, so now that we know how to interpret these two graphs, let's move on to see how step 1 will use these graphs to test you. Do you remember what is a competitive enzyme inhibitor? A competitive inhibitor looks like the substrate and therefore competes with the substrate for the enzyme's active site. Competitive inhibitors can be reversible or irreversible. Reversible inhibitors bind the enzyme's active site but can be easily knocked out by adding more substrate. But irreversible inhibitors bind the enzyme's active site covalently or tightly and cannot be knocked out by adding more substrate. And what about a non-competitive enzyme inhibitor? A non-competitive inhibitor does not look like the substrate and therefore does not compete for the enzyme's active site. Instead, a non-competitive inhibitor will bind a different site on the enzyme altogether, whether or not it has already bound the substrate. The site a non-competitive inhibitor binds is called a regulatory site, and when bound causes reduced enzyme activity. Now let's see how a competitive and non-competitive inhibitor would be plotted on our Michaelis-Menten and Lineweaver-Burke plots. Taking a look at our reversible competitive inhibitor first, why does the Km increase but the Vmax remain unchanged? Let's explain this with our analogy. Again, we have our enzyme bees and our substrate flowers. Our competitive inhibitors in this story will be a bunch of fake flowers or origami flowers. They look similar to the substrate and compete with the real flowers for the bee's active site. Now, with a bunch of origami flowers around, the bees will not know which flowers are real and which are fake. The affinity of the bee for the real flower is reduced, meaning it is harder for the bees and the real flowers to meet up. As a result, less honey will be produced. So, how could we overcome this obstacle and bring our honey production back to normal? Well, we could add more substrate or real flowers to the mix and knock those fake flowers out of the enzyme B's active site. So by doing this, we have increased the Km, the substrate concentration needed to get our enzyme to work at 50% their Vmax. There is no effect on Vmax here because our enzyme concentration and speed that our enzymes convert substrate to product is unaffected, meaning the number of bees is unchanged. They still can produce honey in the same amount of time. Because more substrate is needed to overcome this competition, we say in farm language that the addition of a competitive inhibitor causes a decrease in the potency of the substrate. Taking a look at our non-competitive inhibitor, why does the Vmax decrease and our Km remain unchanged? Again, going back to our analogy, we have our enzyme Bs and our substrate flowers. Our non-competitive inhibitors in this story will be the bee swatter, which can swat our bees whether or not they are bound to a flower. So there is no change in affinity in this situation because the bee swatter does not impact the bee's ability to find and bind the flower. Now, let's not be too cruel to say that the bee swatter kills the bees, but rather it injures them a bit, making them slower and less efficient at producing honey. So with a bunch of bee swatters around, our bees will be sluggish and produce less honey at a given time. Therefore, our Vmax has been reduced. This competition cannot be overcome by increasing the substrate concentration. It doesn't matter if we add more flowers in this story. The swatters damaged our bees' honey-making machinery, and they can no longer produce honey at the same rate. Therefore, Km is unchanged. Because adding a non-competitive inhibitor decreases the rate at which an enzyme produces product, we say in farm language that the non-competitive inhibitor causes a decrease in the efficacy of the enzyme. Interestingly, an irreversible competitive inhibitor will be plotted similarly to the non-competitive inhibitor. However, remember that a competitive inhibitor resembles the substrate and therefore binds the enzyme's active site, while a non-competitive inhibitor does not. Like non-competitive inhibitors, irreversible competitive inhibitors will decrease the Vmax and have no effect on the Km. The reason is due to the irreversible covalent bond formed with the enzyme's active site, making the addition of more substrate pointless because it will not be able to knock the inhibitor away.